Hi everyone. There are two parameterizations of the exponential distribution. Most likely you've come across this one. If we use this one, you see the expected value of x comes out to be 1 over the parameter lambda. If we go over to this parameterization, some of you may have seen, you see it's very similar. It's just instead of having the parameter lambda, you've got 1 over the parameter. 1 over the parameter here, 1 over the parameter here. So there you go, 1 over, say, parameter mu, 1 over parameter mu. If you use this parameterization, you get the expected value equal to mu. And I guess some people like to use this parameterization because then the expected value of x comes out to be something that doesn't involve a fraction, it just looks neater. Okay, so it's entirely up to you which one you use, but for solving any problems you can use either. Okay, so how do you go about calculating expected value of x? Well, the direct method is to write down expected value of x, write down formula. Now since an exponential, if x follows an exponential distribution, this x is continuous. So we use the integral sign. We integrate over the limits of possible values of x. If it's an exponential, the outcomes can take the value from 0 up, so integrate from 0 up to infinity. And then the formula is x fx dx. Substitute for fx, this guy here, and then it is an integration by parts. You've got a function here times another function there. And something like that is done on YouTube videos. So I'm not going to add anything there. Instead, I'm going to show you how you could find this expected value of x without integrating by parts, which would delight my students because even though they might be a clever bunch, they don't get to do much integration in their first year courses, and so they get rusty even though they've learnt it from high school, and that might be you as well. Okay, so how do I do it? It's not an easier way. You've got to know something to be able to apply this method, and the method is this. So I'm going to do it for this one, and then I'm going to leave it for you to do this one if you're interested to show this result using the same method without integration. Okay, let's look at this. Alright, expected value of x, I just substitute now fx, fx, and I take the lambda out because that is a parameter that does not depend on x, which I'm integrating with respect to. I want to find this integral. Alright, now this is no longer a stats problem, it becomes a maths problem, so it's not something I want to spend time on in a stats class, so I'm going to do it now. Okay, so I said we can integrate this by parts, but if we're lazy or if we know something that I'm going to tell you now, we don't have to do that. We don't have to integrate by parts. And it's as follows. We can recognize that this guy here is a PDF of of another distribution. And what you know is that the area under the curve of a PDF must be 1, right? Because that is one of the conditions. Okay, so what is this distribution? That makes this integrate to 1. Well, this is actually it's a gamma distribution with parameters set to certain values. So let's type in gamma distribution into our search engine and look at the Wikipedia page. This is the gamma distribution. Just like the exponential distribution, this also has two parameterizations for the PDF. I can write it like this, or I can write it like this. Now, for my problem, I'm more interested in looking at this because can you see x to the power e to the power of something is very similar to the problem I've got. X to the power of 1 in this case, and then it involves minus my parameter times an x. If I go back to Wikipedia, can you see here it's minus a parameter times x. Let me write it down. Okay, I've just copied this from the site. This is the PDF. The parameters are alpha and beta. This thing here in the denominator is called the gamma function. If alpha is an integer, this is equal to alpha minus 1 factorial. And that's only if it's an integer. Okay, so if x is a whole number. bigger than 0. Okay. So yeah, so the bullet point is that's my PDF. It's from a gamma distribution. This is the gamma function, which is equal to that. And this, using the fact that the area under the PDF comes to 1, is something I'm going to use. Alright, so the thing is, I need to decide now, what do I set the parameters to be, my alpha and beta, to get it looking like this? Well, what happens is this. You set the alpha to 2 and beta set it to lambda. If I set this into here, what I get is this. Now this gamma 2 is going to be 1 factorial. So this fraction has gone. This is like that. Okay, now look at this and compare it to this. Very similar, that this has got an extra lambda squared term. We know that this, since it's a PDF, because it's a gamma distribution, it's going to integrate to 1 over the limits 0 to infinity, because that's the values that x can take if x follows a gamma distribution. And we're integrating because a random variable that is gamma is continuous. Alright, now ready. So the expected value of x is equal, now in red I've just written this again. In blue, what I've done, I've added lambda square here. Why? Because then this is exactly this. But then I have to balance out, so I divide by lambda square. Since it's a constant, I can take this lambda square in the denominator here. I want to leave this up here so you can see quite clearly that this is the same as this gamma. But now the result follows, because that is a PDF, as if from a gamma distribution, it must integrate to 1. Okay, lambda over lambda square, that cancels with lambda squared, so you get to 1 lambda in the bottom. Alright, so the answer is 1 over lambda. Done. Okay, so it's quite a lazy way of solving something like this, but yeah, you don't need integration then. A hint then is, if in stats, is whenever you've got these guys, x to the power of something times e to the minus and then some kind of parameter times x, you should be thinking gamma distribution. Indeed, if you think more closely, the exponential distribution is a form of a gamma. They're both actually part of a gamma distribution with the parameters set to certain values. Okay, so I'll leave that to you to think about, and you can solve for a similar way using this. If you're going to try that, use this parameterization right here. Okay? Okay, well, have a go, and good luck.